slide is pretty important because it does identify all of those individual reactions. You need to be able to look for those pieces and kind of decide what settings you're going to end up using. Okay? With your combination, your decompositions, the textbook will expect you to predict some products because there are some rules as far as predicting those products, which means when we talk about them in lecture, we're going to push you to kind of use those rules. When it comes to the exam, I do not expect you to predict products for combinations and decompositions. I will, however, expect you to predict products for the single replacement, double replacement, and neutralization reactions. We will go through those rules when we get to each of those reactions. Okay? Where we ended yesterday, I think it was this one, we get 3 different types for this type of reaction, 3 different ways we can do this. So if we take this sentence, magnesium metal reacts with oxygen to produce, I'm now asking you to predict the product. Okay? The reason I expect you to be able to predict the product is because you should be able to predict the type of bond between a metal and a nonmetal. Our metal being magnesium and our nonmetal being oxygen. Okay? So let's go ahead and start this out, convert it into an equation. Where do we start? Magnesium. Symbol for magnesium? It's metal, which means phase should be solid. Okay? Reacts with tells us plus. Says oxygen gas. What's our symbol for oxygen? O, and it says gas. Good on the harmony for the 2. Why do we need an extra 2 there? Oxygen is a diatomic molecule. When we're reacting with it, you have to have it in that O2 state. This is then going to go through and produce something. Okay? Any guesses? We're going to form magnesium oxide. So magnesium with oxygen. Because we have now attempted to predict our product, we have to make sure that our product formula is correct. Okay? So our very first step of balancing is to balance each of the individual formulas. We did that with the magnesium metal to begin with, our MgS, our solid here. That was a nice easy one to balance. All we had to do was write Mg. We did it also with our oxygen. That one was a little bit more difficult because it was diatomic. We had to specify the 2. Now when we get to the magnesium oxide, we also have to balance that one. To balance, what are we looking for? Charges. What's the charge on magnesium? It is plus 2. How do you know it's plus 2? It is in the second column on the periodic table, which means it will carry a plus 2 charge. How else would you know magnesium carries a plus 2? Just for those of you that have massive brains. You memorize it. Okay. What's the charge on oxygen? Minus 2. How do we know it's a minus 2? Okay, what's that? So it's not quite a second column issue though. How do we get that 2? It's the 6th column, so why is it not plus 6? Okay. Our charges are ultimately coming from trying to look like the noble gas. If we take a look at oxygen, the closest noble gas is neon. Okay. How do we make oxygen look like neon? We have to add 2 electrons. If we add 2 negatively charged things, what happens to our charge? It becomes negative 2. How else do we know it? You memorized it as well. Okay? So is our formula now balanced? Yes. Our charges balance out. The plus cancels with our minus. Now that we've got our formulas balanced, now we can balance the equation. So we go back through. In theory, you should be erasing any of your work as you, well, kind of erasing any of your work as you go through and attempt these.
The slide I have uses lithium metal reactor bromide gas to produce.
It's one of the later examples.
Okay.
Yes?
Why wouldn't you put a subscript of 2 on oxygen on the second side of the equation?
So the reason you use subscripts is to balance the charge. What was the charge on magnesium?
It was 2 and oxygen was minus 2.
And oxygen was minus 2. If I now put a subscript of 2 on the oxygen, what charge does oxygen contribute? Minus 4. Does my charge balance?
No, but
No.
isn't it doing
Don't you have to what?
Don't you have, doesn't a diatomic doesn't it have to read two?
So oxygen by itself is diatomic. By itself. As soon as we put it into a compound, it is no longer the element oxygen. It is now oxide. It is a different species. We have to be very careful with that, and it's a very easy mistake to make. A lot of people will make that mistake. I'll make that mistake. Okay? So watch out for it. When you try and make your ionic compound, you must balance the charge. Okay? So that is something that you are expected to do. So when we go through and put it together, put the two ions next to each other that need to be there, and then evaluate charge. Okay? So in this case, it was magnesium and oxygen. Then we evaluate charge. Is our charge balanced? Yes. Once the charge is balanced, now we can go back and balance the equation, because your 2 brings up another point. Is our equation balanced right now? No. So we would have to fix that. How do we go through and fix that? Well, same steps that we went through to balance the one up on our board. We'd start with magnesium and say, how many magnesiums do we have? 1. How many magnesiums do we have on our product side? Is our magnesium balanced? Yes. How many oxygens do we have on our reactant side? 2. How many oxygens do we have on our product side? 1. How do we make it 2? 2 in front of the magnesium. Why do we not put it as a coefficient? Or sorry, subscript. Changes that formula, changes that compound. We can't touch that. Once we've balanced the formula, we do not put in any more subscripts. Okay, we can only put in coefficients. Is our oxygen now balanced? Yes, our oxygen is now balanced, so we can be happy. Most people would then skip and say, okay, it's all balanced and move on. Except, as soon as you add an extra number in front of this, you now have the potential to have changed how everything else balanced. So what do you have to do? Go back and check. How many magnesiums are on the reactant side? 1. How many magnesiums are on the product side? 2. Uh-oh, doesn't balance. What do we do? 2 in front of our reactant to make that equal to 2. How many oxygens do we have on the reactant side? How many oxygens do we have on the product side? Does that balance?
Yes.
Yes. We changed a number, so what do we have to do? Go back again. How many magnesiums do we have? 2 and 2. How many oxygens? 2 and 2. What do we do now? Good man. You check it again. Okay? You should check it at least twice where nothing has been changed. Okay? Just in case you're looking at the numbers you wrote and not what the equation is giving you. Okay? We now have our problem balanced out. We could answer coefficients or any other fun kind of questions that might go along with this. What type of reaction do we perform? It is a combination reaction. We took 2 pieces and we smashed them together to make 1. We now have a combination reaction. Okay? Like I said, we have 3 possible types. We have the reaction of a metal with oxygen. We just looked at that. We have the reaction of a nonmetal with oxygen. And we have the reaction of a metal and a nonmetal, which was the last example. So let's take a look at sulfur solid reacting with oxygen gas to produce sulfur dioxide. Okay? What's different about this one in comparison to the last problem? What's that? Both nonmetals. I like that. What else? You're told what the product is. Why are you told what the product is? No, it comes back to your first statement. They're both nonmetals, which means what type of bond do we have? Covalent. You're not expected to be able to predict the their subscripts in a covalent compound. You'll be given that information. So, starting off, what do we have? Sulfur solid. What's our symbol for sulfur? S. I think I heard an SO4 in there. What is SO4? Sulfate. You got to watch out for those endings. They will bite you. It's solid. How do we specify that? So our S reacts of oxygen. The heck? Is that really what that says? I don't know how with was supposed to be of, but can't explain that one. So with oxygen, so the reacts with gives us our plus sign. Oxygen gas, our symbol for oxygen. O, it's gas. Why is it O2? It's diatomic. How do you know it's in its elemental state? We didn't tell you it's not in its elemental state. It's really the only way you'll find out. Okay? If I tell you it's an oxygen atom, then it's just O. Okay? Unless you are specifically told that information, you must assume it's in that elemental state, O2. To produce sulfur dioxide, I like the S and I like the O. Should be SO2. Why is it 2?
Die.
Our dye. So we have to use our nomenclature to apply that. What's the phase? Kind of my bad. Okay. Heard a couple different answers out there. I heard some gases. I heard some solids. How do you know? It would have to be given to you, and somehow or another I didn't include the phase on this one. It is probably a gas. Okay, so let's tweak that. There's our little thing. And say gas.
Because of the O2?
No, not because of the O2. Don't look at it in that respect. So we now have our formula. We could go back and, our equation. We could go back and balance our formulas. Okay? By balancing our formulas, we just have to make sure that the name matches. So sulfur is S, it is solid. Oxygen, to balance oxygen gas, we need 2 oxygens. It has to be O2. To get the sulfur dioxide, what do we balance? We balance from the name. There is no charge, there is no changing of subscripts or superscripts. It's based solely on the name. So the name says there is 1 sulfur and 2 oxygens. Do not mess with that formula. Now we can go through and try and balance our equation. How do we start? Sulfur, how many sulfurs? 1, how many sulfurs? Why is it not 2? Why is it that 2? What are you saying? You're right. The 2 that I just circled only refers to the element immediately in front of it, which is the oxygen. For it to apply to the sulfur, I'd have to include parentheses before that 2, and I don't have those. All right? Our oxygen, how many oxygen do we have? 2, and what does that mean? It's balanced. We can now answer whatever questions we wanted. Okay? Questions about that one? Okay. Lithium metal reacts with bromine gas to produce. So first question is going to be, do I need to do this example? I heard a yes and a no. Sorry, I got to side with the yeses. Lithium metal, I'll go through it faster though. I won't ask for you guys. Lithium metal, which means we're looking at lithium solid, plus bromine gas. Bromine is one of those diatomic elements. Must include that too. To produce, we're looking at a metal and a non-metal. So lithium and bromine, the charge on lithium is a +1. Bromine is a -1. Charges balance. That's good to go. We got lithium bromide. We can now go through and balance the equation. Lithiums, I see 1 on the reactant side. On the product side, I see 1. Reactant side for bromine, I see 2. Product side, I see 1. How do I make 1 equal to 2? 2 in front. Now my bromine's balanced. I go back and check. Lithium, I've got 1. Product side, I have 2. How do I make 1 equal to 2? 2 in front of the lithium. And I should now have it balanced unless I goof something.
What do you do when the charges are different again? You change the subscript?
If you're balancing a formula and the charges are different, you change the subscripts until you balance it out. Exactly right. Sorry? And then you balance the equation. Yep.
Can we do an example of that?
Let me think. The next one is? Yeah. Let's take magnesium metal. So I'm going to put a big line through this. That was an awful color to pick for putting a line through. But magnesium metal, so Mg, solid, plus bromine gas, goes to, Now we're making that metal-nonmetal bond, magnesium and bromine. The charge on magnesium is +2. Charge on bromine is -1. Our charges do not balance. So to fix this, I can now change the subscripts. I'm allowed to change the subscript, that word, because we're balancing the formula. Okay? So that charge needs to now be accounted for. How do I fix that charge? I need 2 bromines. So I can put a 2 as a subscript. Okay? Now, is that 2 the same 2? So let's go through and color these. Is my now purple 2 the same as the red 2 in the reactant? No, they are entirely separate 2s. They have different meanings on where they came from. The 2 from the reactant was because bromine is diatomic, so it must be specified as Br2. The 2 in the product comes because I need 2 bromines to balance out the magnesium. It comes back to fixing the charge. So those 2s are there for very, very different reasons. You must keep those reasons separated. Okay? Once we've balanced the formula, now we can go through and balance everything else. So remember, when you balance the formula, if I give you magnesium bromide, this is going to kind of suck, but I'm going to do it anyway. I don't care where it came from. There is no elemental bromine. There is no magnesium. There is only magnesium bromide. I now must balance that formula. That's where my 2 comes from, is balancing that formula alone. Has nothing to do with where it came from. Okay? Questions about that? Okay. Questions about combination reactions? Done. So, take a look at a new example. Let's heat solid mercury oxide, and when we heat it, it produces mercury metal and oxygen gas. To go through and start this one, where are we going to go? Mercury oxide, what's the symbol for mercury?
HG.
Hg, symbol for oxide. Oh, what's our phase? Our phase is solid. Now we can balance our charge, which you were jumping on.
HG's got a 2 plus.
Hg is +2. How do you know it's +2?
Because the 2 beside it.
The Roman numeral is specifying that. What's the charge on oxide? Oxide, oxygen is a -2 charge. Does our charge balance? Yes. So we can be happy and move on to the rest of our question. When we heat it, it produces mercury metal. So what we're saying is we do a reaction. How do we specify that we've heated it? Include the delta symbol over the top or the triangle to specify that heat. Okay, it produces mercury metal. What is mercury? What's the symbol for mercury? Hg. We're going to specify that we're looking at mercury metal. Looking at it probably in its elemental state. It's a little bit tricky. Mercury liquid, because it's one of our liquids. Okay. And what's the other part of it? Oxygen gas. Why is it O2? Oxygen is a diatomic element. We've now gone through, converted everything into words. We can now go through and start to balance our equation. To balance, we start with, did you say nitrogen? We've got mercury to start. How many mercuries? 1. How many mercuries? 1. Oxygens. 1 versus 2. Is it balanced? How do we fix it? We need to put a 2 in front. As soon as we've changed numbers, we should check and verify. So we go back to our mercury. Is our mercury balanced? We've got 2. I hope that was a phone. And 1. 2 and 1 don't balance. How do we fix it? Put a 2 in front. Our mercuries are now balanced. Our oxygens, oxygen we've got 2 and 2. What do we do now? Check it, go back, check your answer. What do you do after that? Check it again. What type of reaction did we do? Decomposition. We started with one thing and we turned it into two. Most decomposition reactions are initiated with some kind of heat. So as a big tip-off, if you see that delta symbol, you're probably looking at a decomposition reaction. Okay? Oh, I don't know why that's up there, but there's our decomposition. Okay? Go through and give a couple examples. Wow, this is stepping very slow. Other decompositions we could see, you could take a metal hydrogen carbonate and decompose to give a metal carbonate, water, and carbon dioxide. Okay? So in your textbook, they probably gave you a metal carbonate like sodium hydrogen carbonate and says, what does it decompose into? Okay? To do that, how do you figure it out? You have to know the rule. So as far as the textbook's concerned, they assume that you have the textbook and are reading to the directions where it says when a metal hydrogen carbonate decomposes, it turns into these species. Which means follow those rules and predict your answer. On the exam, would I ask you to predict this? No, why not?
We're not going to have access to all the rules.
You won't have access to the rules, which is going to be one of the primary reasons. Decompositions can also be difficult, and I don't expect you to predict those. Okay? So let's go through and balance this one out. Sodium hydrogen carbonate. How do we start with that? Symbol for sodium? Symbol for hydrogen? Symbol for carbonate? CO3. When it decomposes, do our reaction with our little delta symbol, it turns into our metal carbonate. What's our metal? Hydrogen is not a metal. I know it's in a tricky spot. Hydrogen's a weird one. But our metal is sodium. So we get our sodium carbonate. What is carbonate? CO3. Okay, we'll come back to that one in just a second. And water and carbon dioxide are also produced. What's the formula for water? Formula for carbon dioxide. Okay. Before we go on to balance our equation, we must balance our formulas. Yes?
Sometimes, like in equations, they write like HOH instead of H2O.
Mm-hmm.
Does that matter, like how you write it?
HOH versus H2O does not matter. It's purely a perspective thing. Okay? And I'm pretty sure we'll cover some examples today looking at that. Why would we write it out as HOH and not H2O? What is HOH accent? It accents the presence of hydroxide. Okay? So it's merely a formatting thing. Depending on the equation, I'll write it out as HOH as well to kind of accent that hydroxide presence. Okay?
Doesn't it also affect the charge because if you hydrogen has a +1?
Good question. Let's go back and take a look at charge. Okay, so since you've asked it in this case, we're going to start with the last two and work our way forwards. Do we need to worry about the charge in carbon dioxide?
No,
Why not?
because it tells you that it's carbon dioxide, and you just, whatever it is. Oh, no,
It's a polyatomic ion.
If it's an ion, it's charged. Is there a charge on CO2? No. How do you know there's no charge? You're getting to the other answer that we want. How do we know it's not an ion? Upper right-hand corner. Do you see anything written there? No, which means no charge. It can't be a polyatomic ion. There's no charge specified. Back to why do we not worry about charge? What's the bond between carbon and oxygen? It's a covalent bond. Are you concerned about charge with covalent bonds? No, only for ionic bonds. Which brings us to the next issue with water. You mentioned something about charge. And water is one of those ones that can get kind of tricky. Okay? Because we could technically use charge to figure out what was going on within water. We don't need to, though. Why do we not need to worry about the charge with water? What is hydrogen? Non-metal. What is oxygen? Non-metal. What's the bond between hydrogen and oxygen? Covalent. Do we worry about charge with a covalent bond? No. Okay? Which brings us to the next, probably more important issue. We have sodium carbonate. What is sodium?
Metal,
A metal. What is carbonate?
2 nonmetals.
Nonmetals, or polyatomic ion. We now must specify charges and make sure that our formula balances for sodium carbonate. To do that, we have to look at the charge for each of those. What is the charge of sodium?
1.
How do you know it's a +1? It's in the very first column. What is the charge on carbonate?
+4 minus 1. Or no, carbon is it's 1 minus 1. Minus 2.
Carbonate is a -2 charge. How do you know carbonate's a -2? There is only one answer to that question. You memorized it. It is one of the polyatomic ions that I told you to memorize. Okay? If you don't have it memorized, what can you do? Use your textbook. Use references to find out what that charge is. But
I thought carbon was +4 minus 4. So
carbon can be +4 or -4, and technically everywhere in between. Okay?
Oh, you're right.
This is between two nonmetals, the bond between carbon and oxygen. We can't predict our charges on carbon yet. We'll probably be able to predict by the end of the day. Okay? Is our formula balanced? No. How do we balance it? What's the common multiplier between 1 and 2? 2. How do we make 1 equal to 2? Multiply by 2. You'll notice that I changed the subscript. Why am I allowed to change the subscript? Because I'm balancing the formula. I don't care how I got this compound, I have it. Now that I have it, it must be correct. Balance the formula. Okay? How do I make 2 equal to 2? Multiply by 1. So we could put parentheses around the carbonate and say 1. It's a bit redundant, so we typically don't. Okay? We have now balanced all of our individual formulas. We can now go through and balance the equation. Okay? Questions about anything that we did so far? Equation balancing, where do we start? Sodium. How many sodiums do we have on the left? 1. On the right? How do you know it's 2? The subscript. How do we fix that? We need a 2 as a coefficient on our left. What do we move to now? Why carbon and not hydrogen or oxygen? All right, it just has to do with that order of when you apply it. I said that you should do everything before hydrogen and oxygen. It's not going to matter. Okay? Carbon, how many carbons are there? Wow, 1, 2, and 3. There is 1 from the formula, but our 2 applies to everything afterwards. There are 2 carbons there. How many carbons in our product? I only see 1 in sodium carbonate. We also have CO2. We count everything on the product side. So for carbon, we've got 1 plus 1, 2. Do our carbons balance? Yes. Next atom.
Hydrogen.
Hydrogen. Go through and balance our hydrogen. How many hydrogens do we have on our reactant side?
2.
2. How do you know it's 2?
This is the coefficient.
The coefficient applies to everything afterwards. We move to our product side. How many hydrogens?
2.
2. Why do we know 2?
Subscript.
The subscript of our hydrogen there applies forward. Are our hydrogens balanced?
Yes.
What do we move to now? Oxygen. We did carbon. How many oxygens do we have?
3 on the
We end up with a total of 6. We've got the 3 and the 2 applying. So we got 6 oxygens. How many oxygens do we have on our product side? Are you just telling me that? I only see 3.
There's 2, and then there's 1, and there's 3.
There's 3 from our sodium carbonate. There's 1 from our oxygen and 2 from our CO2, which gives us 6. You have to add it up from each source. How's our oxygen balance?
Yep.
What do we do now? What do you do after that? Check it again. Should be balanced, hopefully at this point. You can now answer any questions you wanted to about this. One of the things that we talked about before is I like to balance using the complex ions. I do see the potential for 2 complex ions here. I see hydrogen carbonate, which in my opinion is not really a complex ion, it's just a derivative of the original complex ion, carbonate. Why did we not balance based on carbonate?
It's all on the other side.
What's that?
Because it's only on the reactive side and then it breaks. Oh, never mind.
I made this mistake earlier this morning, so that's why I'm asking it. Carbonate still shows up. Why can I not balance based on carbonate? Where'd the carbon from CO2 come from? Came from a carbonate. One of the carbonates decomposed. When we look at our reaction, we used 2 carbonates. One of the carbonates went into sodium carbonate. What happened to the other one? It was destroyed into water and CO2. So you would have to balance based on the atoms, not based on the complex ion. Okay? So it's okay to balance with complex ions if it shows up the same on both sides. Just realize that you might run into an issue if only one of them decomposed or one of them changed the structure and the other one did not. Okay? So this is one of the benefits of always balancing based on the atom, because if you balance based on the atom, you're always going to be correct. Okay? You could run into more difficulties later down the road, though. Okay? Questions about that one? Okay, the next big example with this one, we can look at metal carbonates decomposing to give a metal oxide and CO2. Do you want me to do this one as well? Yes. I'm probably not going to walk you through it as slowly. I'm going to do it kind of fast. Calcium carbonate decompose into. So to start, calcium carbonate decomposes into. We're looking at a metal oxide. Our metal was, good, fast answer, calcium. Symbol for oxygen. Symbol, sorry, for oxide. Just O, not O2. O2 is for our oxygen. For oxide, we're looking at the ion. It's not its elemental state. Plus CO2. Before we tackle balancing the equation, we must balance our formulas. So we'll go back through with each of these and check. What's the charge on calcium? Plus 2. Charge on carbonate? Minus 2. Do our charges balance? Yes, so we don't have to change any coefficients there. Charge on calcium? Plus 2. Charge on oxygen? Minus 2. Does our charge balance? Yes. Charge on carbon? Do we check carbon? We do not look at carbon and oxygen in CO2 because it's a covalent bond. Okay? We have to balance that formula by making sure that what we wrote matches what was given to us. What was given to us, because I got lazy, was CO2. Okay? We'd probably say carbon dioxide. Okay? Now that our formulas are all balanced, we can go through and balance our equation. We'd start with calcium. Since I want some space, I'm going to do it down below. How many calciums? 1 and 1. Calcium, 1. Can we balance based on the complex ion carbonate? Nope, because it was destroyed, so we'll have to go with carbon. How many carbons? 1. And on the other side, carbons, 1. Oxygen, 3. Oxygen, I only see 2. 1 from our calcium oxide and 2 from our CO2. The total is 3. We must add them together. Okay? Does our formula balance? What do? Check it. Okay? Questions about that one? I'm pausing because I thought there was something else I was going to say. But apparently I can't think of it, so we'll just kind of stick with that. Okay? On an exam, would I expect you to be able to predict these products? No. Remember your decompositions and your combinations. I do not expect you to predict the products. When it comes to the homework, I do expect you to make reference to the rules so that you can go through and determine what those products are, and then go through and balance your equation. Okay? Oops. The one thing I did just remember about it, where did we get our metal carbonate from? What was one of the products of the last reaction we did? It was sodium carbonate, also known as a metal carbonate. If we start with a metal hydrogen carbonate and heat it, it turns into a metal carbonate, water, and CO2. If we heat it even further, what happens? It decomposes a second time into more CO2 and our metal oxide. Okay, so our hydrogen carbonate compounds could go through 2 decomposition reactions, depending on how long we heated it for. Okay? Questions about our decoms?
So on the exam, you would give us the whole thing?
I'd give you the whole thing and ask you to balance it. Yep. Okay. We were done with questions on that, right? Okay. We will see some more balancing. So, new problem. Iron solid is mixed with aqueous copper sulfate solution. Okay. We are now moving into the realm of being or needing to be able to predict reactions with some caveats. This is actually a bad, I didn't actually pick awful examples because none of these I would expect you to be able to predict your products for. But we'll talk about that as we go through it. Iron solid, symbol for iron, Fe. It's solid, so put the S. Why do we not put a subscript 2? Iron is not a diatomic molecule. We don't specify that. Okay? Plus our aqueous copper sulfate solution. Oh, wow, I did a horrible job with this example. I apologize. We'll address each of these issues as we hit it. So we've got copper sulfate and our aqueous. What was the issue? What's the charge on copper? It's 1 or 2. How would that be specified to you? You would have to see it in a Roman numeral that was not included in this one. Okay, so that would have to be there.
Is that why you're saying you did a horrible job?
Yeah, picking a problem, yeah. In my half defense, I'm going to say I copied it from the old slides, but that's probably not true. What we're now going to go through and do is what's known as a single replacement reaction. So what we're going to do is take the metal ions, or the metal atoms, our iron and our copper, and we're going to have them swap places. Okay, so we're doing a replacement. We're only swapping the place around one anion, so we are doing a single replacement. So if we go through and look at the product, we generate iron sulfate, and we'll have copper. Some extra little pieces that come out of this. To start off a single replacement reaction, one of our metals will be in its elemental state. To end a single replacement reaction, the other metal will be in its elemental state. Okay? So we see a complete swap. We don't end up with those metal ions. Okay? What happens to iron in the course of the reaction? Well, what's its state to initially? What's its charge? What's the charge on iron solid? Right here. What was that? No. Where do you see charge? Upper right-hand corner. What's written there? Nothing. What's the charge on iron solid? 0. The charge of iron or anything in its elemental state is 0. What's the charge on iron and iron sulfate? Now it's 2. How do you know it's plus 2? What's that?
Because
No.
sulfate is a plus 2.
Sulfate is a minus 2 charge. For this to have an overall charge of 0, iron must be a plus 2. Okay? Which brings up the next issue with this. How would you know, if I asked you to predict the products, what the charge was on iron? If it's variable, you wouldn't be able to predict it. Okay? I would have to tell you that you are forming iron in its plus 2 state. Now balance. Okay? So just kind of be aware of some of the limitations within these. Okay? I will come up with an example probably on the quiz that you'll take on Thursday where you will be able to balance without knowing all those charges. Okay? So now the next question. Does this reaction actually occur? How would you decide that it, well, let's see, how much information do I give? Okay, single replacement reaction. So we're looking at a single replacement here. You are expected to be able to predict these under very particular circumstances. You should at least be able to predict the ion swap. You may not be able to balance your formulas if you don't know the charges on those metals. Okay? But how do you predict that this reaction actually occurred? If I add iron to a copper solution, does it react? Okay, this equation says yes, but how would we know that?
Memorize it.
Kind of, sort of.
In the book, wasn't there a list of what reacts with sort of?
What we would do is go to the lab and we would test it. The lab that you are doing this week is generating this information, deciding how those individual metals interact. Okay? And what the textbook refers to it as is the activity series. Okay? And almost every book will refer to it as an activity series. Most books do a much better job of presenting it. Your textbook is awful. Okay? Because it goes through and instead of listing it as a nice, the highest is the most reactive and the lowest is the least reactive, it condenses it into this stupid table that runs on top of itself. Okay? So it's very difficult to interpret. Okay? Other versions, not to say I'm that much better, because I probably snagged this from somewhere else, organize it in a nice vertical column. Okay? So what we've done is put the most active metal at the top and the least active metal at the bottom. Okay? We still have to be able to interpret this, but this is a way of organizing if that reaction can occur or not. Okay? So let's go through with a couple examples that maybe we know something about. Let's pick gold and let's pick lithium. What happens when I put gold into water? No, it sinks to the bottom of the container. Okay, that was pretty boring. What happens when I throw lithium metal into water? We get a very violent reaction. Okay? That's what our activity series is ranking. Lithium really wants to react. So it has the most activity. How is it reacting in the course of that reaction? It is trying to become an ion. So what our activity series measures is the desire of an individual metal to be in its ionic state, okay, to have charge. Gold at the very bottom does not want to have charge. Does that make physical sense? What is our standard of currency? What is all money throughout the entire planet based off of? Gold. What's another valuable material that we... Silver. What's another one? Platinum. Notice where silver, platinum, and gold are on the activity series. They are at the very bottom of the series, meaning they do not want to be ions. They are not easy to turn out of their metal state. Why would that then apply back to our putting value on that material? Well, if I decide that my currency is based on lithium, I now have 500 pounds of lithium. That's awesome. Let's just say I'm a billionaire. Okay? Someone doesn't like me very much and says, you know what? Your lithium currency sucks. Here's some water. Have fun. At the end of that, if I based my currency off of lithium, how much lithium do I have? None. Okay? So we tend to base our values in our monetary system off of things that do not change. Gold, silver, and platinum are all materials that do not react and do not readily change their shape, their composition on their own. Which means if I take a vault and I throw gold into it, in 100 years, I should be able to come back and have the exact same amount of gold. So I can use that as a way to measure my monetary value. Okay? So that's one of the repercussions, I guess, if you will, of our activity series. We put a lot of emphasis in the bottom of that activity series because they don't change their physical state. I know you had a question. Yeah.
Yes. So would we know that lithium reacts with water because it's above hydrogen, and hydrogen is a component of water?
We'll look at water in a little bit. It's a special case. Okay? Sort of. So let's take this activity series and now apply it back to the question that we had. Would we expect a reaction? So what I want to go through and do with this reaction is find the metals that are in their ionic state. So what metals am I looking at? Copper and iron. Okay. So now I go back to my activity series and find copper and iron on my activity series. Apparently I'm having trouble reading today. There's copper. There's iron. Iron is above copper on the activity series, which means it has a greater desire to be an ion instead of copper. Okay? So we now go back to our reaction. Iron wants to be an ion. Which side of the reaction is iron and ion? Where is iron and ion? Where is it charged? Iron has a +2 charge there. Iron charged is on the product side. How do I get iron to be an ion? Does the reaction work or does it not? It must work. Otherwise, I don't have iron-ion. So I use the activity series to predict that this reaction does indeed progress forwards. I do expect to see copper solid come out of that solution.
So if you can see that an ion has been produced on the product side, you know that there's a reaction.
No. Every single reaction will produce an ion on the product side. Every single one. What you have to do is base it off of the activity series. We'll look at a couple more examples here. Okay? So let's start with our iron in the presence of HCl. This is an interesting one. Okay? It's an interesting one because we've got our first metal as iron and our second metal is chlorine, a metal? No, chlorine's not a metal. Is hydrogen a metal? No. What the heck is going on here? Take a look back at the activity series. Capital letters, nice little star next to it. Hydrogen. Why is hydrogen a non-metal showing up in our activity series? When we're looking at our activity series, it's not just the reactivity of metals. What we're looking at is any species' desire to become an ion, okay, or change electrons. Every atom has an ability to be measured in this case. Every molecule has an ability to be measured in this case. What we're looking at here is a very shortened, modified version of something known as the standard reduction potential. Why do we not look at the standard reduction potentials then? How many of you like numbers? Yeah, 2 out of the class. The reduction potential brings in a lot more numbers. The activity series allows us to qualitatively do the analysis that we need without having to look at numbers. We need to be able to generate some way to get these numbers. Okay? To do that, we have to have a 0 point on which we can compare everything. Hydrogen is that 0 point. Okay? So our activity series technically has all sorts of other things in it, nonmetals as well. We don't include them to simplify it, make life a little bit easier to interpret, but we do need to include the hydrogen because that is our 0. That is from which everything is compared against. Okay? So when we go through and take a look at this next reaction, we are reacting iron, and we're going to do the single replacement with hydrogen. Okay? Iron goes to a cation, hydrogen goes to a cation. They're both positively charged species. So what we are doing is converting those two. So if we go through and complete our reaction, we would generate iron chloride and hydrogen all by itself. Hydrogen all by itself needs to be diatomic, has to be H2. Okay? Next issue is balancing. We just looked at balancing our hydrogen formula. Now balancing the iron chloride formula. How do we balance that one? What's the charge on chloride? You know it's -1 because 7th column, 1 more electron, it looks like a noble gas. What's iron? We can get 2, we could get 3, we get all sorts of charges. We'd have to, again, specify this. I will tell you right now that the iron, for the sake of this question, is an iron +2. Is our formula balanced? No. How do we fix it? It needs to be FeCl2. Is that 2 on the chlorine because chlorine is diatomic? No, that 2 on the chlorine is to balance out the iron. It has nothing to do with the diatomic species of chlorine. Okay? We now have our formulas balanced, so we could go through and balance our equation. Our irons balance out. We get 1 and 1. Hydrogen, we get 2 and 2. Chlorine, we get 2 and 2. Balances out. So I partially balanced it with that 2 already for you. Not quite sure why I did that. So we now have our balanced equation. Now we can go through and start to evaluate if this reaction occurs. So what were our 2 species that exchanged electrons? Hydrogen and iron. So we go back to our activity series. We've got hydrogen and we have iron. Which one is higher on the activity series? Iron. What does that mean? Iron prefers to be an ion. So we now go to our reaction. Where is iron an ion? On the product side. How does iron become the ion? Does the reaction occur or not? Yes, it must occur. This reaction occurs, and we see hydrogen gas formed. Okay? Questions about that one? You ready to see one that doesn't work? Okay, let's take a look at our next one here. Gold and sulfuric acid. What are our metals, if you will, with quotes? Gold and hydrogen. This is where I'm going to differ from the textbook. The textbook, particularly if you look up answers at the back of the book, for this one just say no reaction. They don't show how to balance this reaction. I think that's an awful idea. Balance it out anyway. Predict and see what happens. Gold will exchange with our hydrogen. So we're looking at hydrogen and sulfate. So our gold is going to completely swap for all the hydrogens, and we'll end up with gold sulfate. Hydrogen is then going to be left off on its own. So we'd get H. Why does it H2? Because it's diatomic. Does it have anything to do with the fact that there's a 2 there? No. Remember, different purposes. Okay? Now that we've got our formula, I'm going to tell you, though it's wrong, that gold has a +2 charge. Why would I tell you gold has a +2 charge? Because that makes this balance really, really easily. You should be able to go through and see that this equation is indeed balanced. Okay? We'll now go through and identify our 2 metals that exchange places. We've got our gold and our, whoops, I don't want to do it there. I want to circle where they're in their ionic state. Our hydrogen and our gold. Go back to our table. We've got hydrogen and gold. Which one's higher on the activity series? Hydrogen, which means hydrogen wants to be an ion. Which side of the equation does hydrogen have an ionic state? The reactant side, hydrogen is a +1. On the product side, what is our charge on hydrogen? 0, upper right-hand corner. Where is hydrogen an ion? The reactant side. Okay? What does that mean about the reaction? I mix gold solid with this sulfuric acid. What occurs? Nothing happens. Preferentially, hydrogen wants to stay or wants to be an ion, more so than gold. Hydrogen starts in its ionic state. If it starts there, it's not going to change. Okay? When we compare it back to the gold. So the end result for this, and this is where I think you lose a lot of information, is your textbook goes through and erases all of that and just says, no reaction. Okay? Why do I go through and balance out the whole reaction? Because I personally find the activity series confusing. I get it backwards all the time. The only way that I can make sense of it is I have something that I can directly look at and line up and match and work with. Your textbook goes through and does a massive shortcut and effectively has you compare gold and hydrogen in your head back to the activity series. So you have to balance the reaction in your head, now compare your activity series, and then go back and decide, is there a reaction or not? To me, I just did 4 steps, all in my head, almost guaranteed I'm going to mess one of those up. If I put the information down on paper, I can at least see it and see if there's a mistake a little bit more immediately. Okay, so it helps me out a lot. Questions about that?
Are we going to need to memorize the activity series?
Next click. I know it's not quite as dramatic in the upper left-hand corner there. It says, I will give you a condensed activity series. Okay? It will probably not be as long as this. It will definitely not be in the format the textbook gives you. It'll be in this straight vertical line. Nice little table like that. My guess would be 5 to 10 elements. So all the elements that you would need to use, and then probably a few extras just to be in the way. Okay? You guys think you got that one on your own now? Seeing some yeses, so we'll leave that. No? Okay. So let's take a look at the last one. Yeah, we can take a look at the last one.
I'm just not getting how to see if it's reacting or not reacting. I mean, when I was doing the homework, that was one of the questions I asked.
Okay, so again, we'll go through my method. Predict the products. What are our metals for this last one? Gold and copper, which means we're going to do our single replacement. We're going to end up with gold sulfate and copper solid. Okay, elemental state. Again, I'll tell you that the gold in this case is again +2, which is technically wrong, but again, ignore it. Why do we say +2? Our equation's now balanced, so nice and neat for us. Okay. Now what we want to do is decide and predict should this reaction occur. To do that, we have to go back and look at the activity series. Okay? Before we get to the activity series, we have to know what metals are reacting. What are our metals that are doing anything? We're looking at copper and gold. Notice that I'm still circling very consistently the same types of elements. I'm circling the metals that are in their ionic state. Copper with sulfate is a +2 charge. Gold with sulfate is a +2 charge. Okay? Gold by itself is 0. Copper by itself is 0. I want to look at the ions because how I interpret the activity series has to do with those ions. Okay? So I'm looking for copper and for gold. So back to the activity series and circle them. Gold is at the bottom, copper is a little ways up. Okay? Which one is higher on the activity series? Copper. What does that mean?
Copper's going to react.
I don't want to hear react. Nope. Copper wants to be an ion. It has nothing to do with whether the reaction's occurring or not. Copper wants to be the ion. Okay? So if I'm going to compare these two, copper and gold, the side of my reaction that has copper as an ion is going to be the side that works. So now let's go back to the reaction. Where is copper an ion? It is on the reactant side. So now I take these two things, my copper solution and the gold, and I mix them. Copper is in its ionic state. Does copper want to be in an ionic state? Yes. If I start ionic and I want to be ionic, am I going to do anything else? Absolutely not. Because I'm already where I want to be. Would I expect a reaction? No. It's already happy. It does not want to change its state. It's already in the state it needs to be in. So the end result of this, no reaction. Okay? And that whole wants to react, not wants to react, is what confuses the crap out of me. Go back to the ions. If it's higher, it wants to be an ion. Go to your equation. Where is it an ion? Whatever side of the reaction it's an ion, that side is going to happen. Okay? If it's on the product side, so if we go through and compare, because now we've looked at two non-reactions. Does it sound like I'm losing my voice? Because it really feels like it. If we go up to the top one, we've got our copper and our iron. +2 and +2. Where are copper and iron? There's copper, there's iron. Which one's higher on the activity series? Iron. What does that mean? It wants to be the ion. Go back to the equation. Where is iron an ion? On the product side. How can I get iron to be a product? Does the reaction occur?
Yes.
The only way I can get iron to be an ion is if the reaction occurs. So a reaction does occur.
Does it occur because it's on the product side?
It's on the product side.
That's why it occurs. But if
Yep.
it's on the
If it's on the reactant side,
then it doesn't.
there's no reaction because it's starting already at its stable state, where exactly it wants to be.
So if it's on the product side as an ion, and we know that it's an ion because it's attached to the
Non-metals.
non-metal, then what did I just say? If it's on the product side and it's attached to the non-metal, then you know it reacts because it's an ion.
If it's higher on the activity series. It all comes back to the activity series. You can't just say there's an ion on the product side, it must work. No. You must relate it back to the activity series. Take a look at the last reaction. Gold is an ion. In that last reaction, if we look at our product side, gold is an ion. According to what you just said, gold is an ion. On the product side, it works. No. Why does it not work? Why does it not work? So what you're missing is you're not applying the activity series. You must apply the activity series first to decide which ion needs to be an ion. So in this last case, we're comparing copper to gold. Which is higher on the activity series? Copper. Which one prefers to be an ion? Copper. The only ion I care about now is?
Copper.
Copper. Where is copper?
Reactant.
Reactant side. Does a reaction occur?
No.
No. Take a look at the top reaction. Our metals, man, oh. Copper versus iron. Maybe I'm shouting. Maybe I should be quieter. Copper versus iron. What? That just stopped working. Copper versus iron. Okay? We compare them on our activity series. Which one's higher on it?
Iron.
Iron. Iron wants to be the ion. Where is iron and ion?
Product.
On the product side. How do we get to be a product? We must run the reaction. Okay? So what you've been leaving out is the interpretation of the activity series. You have to include that. Without that interpretation, you will get the answer wrong half the time.
I think if I practice it, I'll put it together.
Okay? So, we'll see what happens. This comes back to your water thing. They mention active metals. I don't really want to spend any time on it. Some of the metals at the very top of your activity series are so reactive, so much want to become an ion, that when we throw them even into a water solution, they react. Why might they react in a water solution? Well, the other way that we could write out H2O, whoops, whoa, come back here, was HOH. They're reacting with hydrogen. Okay? The difference is that the hydrogen in H2O is not as reactive as the hydrogen in, say, sulfuric acid. And we'll discuss that much later in the semester. Okay? So, special case, some elements react crazy with water, some don't. You don't need to know which elements, you just be aware that it does pop up. Okay? So what we're going to get into now very, very quickly is the oxidation and reduction chapter, so chapter 17. The reason we're going to talk about chapter 17 in this case has to do with that reaction we just looked at. We looked at iron. Okay, what happened to our iron? What's its charge in the starting material? 0. What's its charge in the product? +2. How did it do that? It lost 2 electrons. Remember, we cannot create or destroy matter. Electrons are matter. So in the course of this reaction, we have to account for where those electrons went. What we're looking at is the transfer of electrons between atoms, and that is known as oxidation and reduction, or better phrased, as you'll hear by me, redox reactions. Okay? So it's all about the transfer of electrons back and forth. We're going to introduce a new concept here. We're going to call it the oxidation state versus the charge. Okay? It's kind of a tricky concept because they overlap in a lot of cases. The oxidation state or number will only apply to an atom, and an atom alone, just one. The charge applies to a unit. That unit could be a single atom, it could be a molecule, it could be a polyatomic ion. That unit can be a whole variety of different things. Okay? What you have to realize is that these two concepts are separate. The oxidation state only applies to the atom, charge applies to your unit. Okay? There are certain rules, and again, I will go over these. I want to hit some examples on this. There are rules behind your oxidation numbers. We've already addressed some of them. Elements are always have a 0 oxidation state. Monatomic ions, their oxidation state will be the same as their charge. Okay? The next big rules, and these ones are really important, oxygen will always have a -2 charge. There is an exception, but we won't worry about that. Hydrogen will usually have a +1 charge. We might see that exception, so we won't mention that. It could possibly have a -1. Halides will always be -1 unless they're bound to oxygen. The biggest lesson out of this would be 4. The sum of the oxidation numbers. So when we sum up the oxidation numbers of all of our atoms within an individual unit, that must equal the charge on that unit. Okay? So here's the slide I really wanted to hit. Like I said, I will cover this again because I know I'm doing it very fast. If we look at the charge for each of those examples up in blue, where's the charge specified? Upper right-hand corner. So the charge for our copper ion is +2. Copper, it's 0. For nitrate, it's -1. For sulfate, it's -2. How would you know those charges? It's either there, good answer, or 2, you had them memorized. Okay? So you would need to know some of that information. So we've got those charges for each of those units. Oxidation state, and this is where it becomes confusing. Our oxidation state must be derived from this formula. The oxidation state times the number of the element plus the number of the element times the oxidation state plus the number of the element times the oxidation state, so on and so forth, must equal the overall charge. So when we look at the oxidation state for copper metal, what is it? Well, we said it must be solved for. There is no exception. You must solve for it. So how many copper atoms are in copper metal? In our formula right there. 1. Right? What's its oxidation state? We said we have to solve for that. Equals
0.
Overall charge. 0. How do you know it's 0? Upper right-hand corner, it's 0. What is the oxidation state for copper? 0. Copper in its elemental state has an oxidation state of 0. We derived rule number 1 from our previous slide. What's the oxidation state for copper +2? +2. What's the oxidation state in nitrate? Trick question. Oxidation state applies to atoms. Only atoms. When you look at nitrate, there are 2 atoms. You have to solve for the oxidation state for both of them. Okay? The big rule that you need to know, oxygen will always be a -2. If you set up the formula, you should be able to solve for nitrogen coming out at a +5 and the sulfur coming out as a +6 with those. We will go back over those, and you will probably get quizzed on those on Thursday. We did not get to the quiz, but we at least covered all the material that we got in the morning too. All right?
You